The time has come. We have found the first traces of life in space. The James Webb Telescope has discovered a planet that is even more suitable for life than Earth. Biomarkers in the atmosphere of the exoplanet K2-18b indicate that this world is covered by a vast ocean. But how can we now find out whether intelligent life exists there? James Webb and other observatories provide clues, and if so, could we ever reach K2-18b? The search for exoplanets is in full swing. The James Webb Space Telescope, a new star observer in the night sky, is not only supposed to search for the beginning of time but also to take a closer look at exoplanets. We have only been able to detect other planets in space since 1995. They are so tiny that our telescopes were not good enough to find them. For example, take a look at this image of Earth taken by Voyager 1 in the early 1990s. Earth appears as just a dot, nothing more, and Voyager 1 was still within the solar system, only 6 billion kilometers from Earth. It is at least 4.132 trillion kilometers to the nearest stars in the Alpha Centauri system. This gives you an idea of how tiny planets are in the vastness of the cosmos. Tracking them down has long been like detective work. Scientists use a trick to spot these tiny planets. They become visible when they pass in front of their stars. This type of exoplanet detection is called the transit method. Another method detects planets by observing minute gravitational shifts caused by the planets in the movements of their stars. Both methods are not always entirely reliable, but scientists have been able to identify more than 5,000 exoplanets. However, if we want to know whether there are worlds similar to ours, another hurdle arises. It has not yet been possible to determine parameters, such as the presence of an atmosphere or water. Until recently, we could only get a rough idea of whether these exoplanets were heavy, massive rocky planets or less dense gas giants. Since the James Webb Telescope has been in use, this has changed. This super telescope can use light reflections from a planet to determine whether water and other biomarkers are present. Imagine the joy when James Webb found signs of life in the atmosphere of an exoplanet for the first time, methane and carbon dioxide in the atmosphere of K2-18b. The James Webb Space Telescope, JWST, is a true masterpiece of modern astronomy. It houses some of the most advanced instruments ever sent into space, with the unique ability to detect and analyze exoplanets. The wealth of data and precise measurements go far beyond scientists' wildest dreams. At the forefront of its equipment is the Near-Infrared Camera, NIRCam, specially designed for observations in the near-infrared range. This eye of the telescope can capture the faintest light signals from stars in distant galaxies. NIRCam is key to identifying exoplanets orbiting their stars. The Near-Infrared Spectrograph, NIRSpec, breaks down the light from stars and planets into its individual colors. This spectral analysis helps scientists understand the chemical composition of exoplanets and their atmospheres. Each element and gas has its own unique light signature, which James Webb can capture and analyze even across vast distances. Thanks to this technical marvel, we can now peer into the atmospheres of distant worlds and reveal their secrets. The Mid-Infrared Instrument, MIRI, further refines the telescope's capabilities. It provides information on wavelength ranges of light invisible to the human eye, detecting the thermal radiation of cooler objects such as newly formed stars or dusty disks around young stars. MIRI can even determine the heat of exoplanets and potentially reveal weather phenomena. Let's take a closer look at the surprising data James Webb has collected around the exoplanet K2-18b. Through its advanced instruments, the telescope's analysis of the planet's atmosphere revealed clear evidence of carbonaceous molecules, particularly methane and carbon dioxide. These molecules are highly significant because carbon is a key element for life, acting as the backbone for all known life forms on Earth. The presence of carbon-containing molecules in a planet's atmosphere is often considered an indication of potential biological processes. On Earth, methane is primarily produced by biological activity, such as the digestive processes of living organisms or the breakdown of organic matter. Its detection in K2-18b's atmosphere could similarly suggest biological activity on this distant exoplanet. Although methane can also be produced by non-biological processes, such as volcanic activity, the combination of methane and carbon dioxide found in K2-18b's atmosphere makes it an even more compelling candidate for life. These biomarkers are exciting clues that raise the possibility of biological processes occurring on K2-18b, and future observations will help scientists confirm whether life might exist there. This discovery not only expands our understanding of distant worlds, but also fuels hope in the search for extraterrestrial life. Methane is a simple molecule made up of one carbon atom and four hydrogen atoms. On Earth, methane is mostly produced by biological processes, such as digestion or decomposition. While methane can also be produced by geological processes, its presence in a planet's atmosphere is a strong indication of possible biological activity. We all exhale carbon dioxide, and it is also produced in industrial processes. However, on K2-18b, carbon dioxide could indicate cellular respiration, another potential biomarker. Carbon dioxide alone is not necessarily evidence of life, as it can also be released by non-biological processes like volcanism. However, if we take a closer look at K2-18b, we can rule out volcanism as the cause. In the search for life, the ratio of carbon dioxide to other gases in the atmosphere is crucial. If several biomarkers are found in combination, the chances of life existing there increase. Imagine a world about 2.6 times the size of Earth, covered by a vast ocean. These are the Heen worlds, which represent a new category of planets and fascinate researchers. Known scientifically as subneptunian planets, these water worlds could provide rich environments for life. The James Webb Space Telescope has made a groundbreaking discovery on the exoplanet K2-18b, uncovering large quantities of water and a hydrogen-rich atmosphere. These findings suggest that K2-18b could host a vast ocean, potentially making it a habitat for life. Located about 120 light-years from Earth, K2-18b orbits within the habitable zone of its parent star, K2-18, a cool dwarf star. The planet has 8.6 times the mass of Earth, placing it in the size range between Earth and Neptune, often referred to as a mini-Neptune. What makes this discovery even more intriguing is the chemical composition of K2-18b's atmosphere. Scientists have detected high levels of methane and carbon dioxide, both of which are considered potential biomarkers. The absence of ammonia further supports the hypothesis that the planet has a water ocean beneath its thick hydrogen-rich atmosphere. This unique combination of factors increases the possibility that K2-18b could support life, either in the form of microorganisms or more complex aquatic life. While much remains to be studied, this discovery marks an exciting step in the ongoing search for life beyond our planet, as K2-18b presents one of the most promising environments for habitability discovered so far. James Webb also found another exciting clue, a molecule called dimethyl sulfide, DMS. On Earth, DMS is only produced by life, with most of it coming from phytoplankton in marine environments. Upcoming observations by Webb should confirm these data, and if they do, we will likely know with great certainty that biological life exists on K2-18b. This could include simple life forms such as plankton, algae, and microorganisms, but complex life, such as fish or aquatic mammals, could also be possible. Moreover, we must always consider the possibility that there are life forms on other planets that we cannot even imagine. Even on a planet completely covered by water, higher life forms might have adapted to life in the ocean. Whether K2-18b has land masses is still unclear. Determining this from such a great distance is indeed difficult. However, what is exciting is that James Webb's instruments might be able to detect artificial light emissions, such as those from cities on a distant planet, which would greatly advance our search for extraterrestrial life. K2-18b was not initially discovered by James Webb. The first insights into the atmospheric properties of this exoplanet came from observations with the Hubble Space Telescope. These data were so promising that researchers were eager to take a closer look at this world with the newer James Webb Telescope, and their enthusiasm was rewarded. The analyses surrounding K2-18b are fascinating and might represent our first discovery of traces of life in space. This potential discovery is a sensation, as humanity has been searching for other forms of life for nearly 100 years with no success. Nowhere in our solar system have life forms been found, though the icy moons orbiting Jupiter and Saturn are still considered possible places to find them. Researchers believe that Heen exoplanets could be true superworlds and birthplaces of rich life. Life on Earth also began in water, with land masses and mammals emerging only much later. If Earth had remained a water planet, intelligent life forms living entirely in the ocean might have developed. Traditionally, the search for life in space has focused on exoplanets similar to Earth, smaller, rocky planets. However, the larger Heen worlds are now being considered as real superworlds in the cosmos. While some researchers remain cautious, fearing the oceans on these planets might be too hot or uninhabitable, others point out that life in Earth's own hot, toxic thermal pools, like those in Yellowstone Park, proves that life can thrive even in extreme environments. Of course, there's the exciting question of whether we can ever definitively know whether K2-18b is inhabited. If we were to find evidence of intelligent life, we would naturally want to make contact. However, K2-18b is about 120 light-years away from Earth, representing an enormous challenge for current space travel technology. Presently, it takes years for our probes to reach destinations millions or billions of kilometers away. A planet 120 light-years away, or even one as close as 4 light-years, would be far beyond our reach with current propulsion technology. The Voyager probes, launched in the 1970s, will take thousands of years to reach the nearest star systems. If we were to make contact with a species somewhere in space, we would need to get inventive. The discovery of Earth-like planets in the neighboring Proxima Centauri system inspired space enthusiast Yuri Milner to design nanospaceships that could travel near the speed of light. These mini-probes, equipped with cameras, are expected to cover several trillion kilometers in just a few years, delivering photographs of planets that may harbor life. If we were to discover a civilization in space, it would likely spur new ideas and innovations among scientists. Such ambitious goals drive our spirit of research. If one day we develop warp drive technology and can move through the universe by folding spacetime, traveling to worlds like K2-18b would no longer be a problem. But for now, our spacecraft still operate within the limitations of Newtonian physics, relying on acceleration through propellants and fuel. Even if we could build a spacecraft capable of traveling at 10% of the speed of light, the journey to K2-18b would take 1,240 years. Even a radio signal, which travels at the speed of light, would take 124 years to reach K2-18b. A response to such a signal would take another 124 years to return to Earth, making any form of communication slow and challenging.